Welcome everybody to this term's unique Oxford Discrete Maths and Probability seminar. It's lovely to have so many people in the audience. We're really pleased to have Rongfeng Sun joining us from Singapore. It's a great pleasure to see you again after a very long time, and lovely to have you speak in our seminar. So the usual situation applies. If anybody would like to ask a question, please feel free to ask in the chat and we'll alert Rongfeng, or feel free to unmute yourself and just ask if you would prefer. Over to you, Rongfeng.
Okay, yeah, thanks to Christina and Alex for the invitation. And so it's a pleasure to give this seminar online. So I'll talk about the random spanning tree in running environments. Okay, is everything clear? Okay. So here are my collaborators. And so Luca is in the audience. And Michele is currently teaching, but he said that he'll try to join after he finishes teaching. So at the end, if you have questions, you can direct them to Luca and Michele. Okay, so here is a brief outline of what I plan to talk about. So first, I will give basically an introduction to background on uniform spanning trees and minimum spanning trees. Then I will introduce the model that we studied that is called we call the random spanning tree in running environments. And okay. And and then I'll talk about the main result, which is on the diameter of the random spanning tree in running environment. So we'll discuss the low disorder regime and the high disorder regime. And then I will explain some key ideas in the proof and also some results by Luca on the local observables. And then I'll conclude with some open questions. So just a reminder of what is a uniform spanning tree. So if you are given a graph, say a connected graph G with a vertex set V and the edge set E, so for example, here I'm just looking at this graph, then a spanning tree is basically a subgraph, which is a single tree that contains all the vertices. So there are no loops. So here is an enumeration of all the possible spanning trees of this graph. And so we are going to denote by the set by TG, the set of spanning trees of this graph G. So the uniform spanning tree just means that I sample a tree at random from this set TG. So every spanning tree is chosen with equal probability among the set of all spanning trees. So that's the uniform spanning tree. And so just now I introduced the uniform spanning tree on just a graph without introducing any weights on the edges. So you can generalize the idea of uniform spanning tree to a uniform spanning tree on the weighted graph. Or alternatively, you can think of the weights as conductances on the edges so that you can associate it with a random walk on the conductance network. So in this case, the uniform spanning tree on the weighted graph is defined as follows. So given a spanning tree, the probability that you sample this tree is basically proportional to the product of the edge weights on the edges of the tree. And if you do that, then you need to normalize it to be a probability measure. So that's why we divide by the so-called partition function. And so that defines the uniform spanning tree on the weighted graph. So closely related to uniform spanning tree on this weighted graph or on any graph is the notion of a random walk on this graph or random walk on the conductance network. So in this setting, we interpret the edge weights as conductances. So if you look at the random walk on this conductance network, then the transition probability is defined as follows. Suppose you start from the vertex X, and you want to know what's the probability that you cross the edge connecting from X to Y. So the transition probability is proportional to the conductance of this edge. And so to make the probability measure, you should normalize it by the summation of all the conductances incident to the vertex X. So if you're on the usual graph, then it just means that you choose one of the incident edges with equal probability, and then you cross that edge. So that's the random walk on this weighted graph or on this conductance network. So one of the classic results of sampling uniform spanning tree are the following. So there are two algorithms I want to mention. And one is the so-called Aldous Broder algorithm. So in this case, in order to sample uniform spanning tree on this weighted graph, what we do is that we run a random walk X on this weighted graph based on these transition probabilities I just specified until all vertices have been visited. So this is the time when you cover all the vertices. And so whenever a vertex is visited by the random walk for the first time, it must have traversed a particular edge which is entering that vertex. So therefore, we add that edge to your tree. And so if you do that for every vertex, then you're going to get a spanning tree. And it turned out that the distribution of this spanning tree is exactly the uniform spanning tree on this weighted graph. So that is the so-called Aldous Broder algorithm. And then there is a second algorithm, which is called the Wilson's algorithm. So in this algorithm, we fix an arbitrary ordering of the vertices. You just label the vertices by n order, 1, 2, 3, etc. And what you do is that you start with, you're going to build the tree recursively. So you start with the first vertex, let's call it V0. And then what we are going to do is that you start with the vertex, and then you start, so the V0 and the V1. So starting from V1, you are going to run a loop erased random walk until it hits V0. So loop erased just means that whenever it creates a loop, chronologically, you're going to erase the loop. And then therefore you create a branch connecting from V1 to V0. So that's the next step of your construction of the tree. And then if you start from V2, and then you run the loop erase random walk until you hit the tree that you have constructed. And so you erase all the loops along the way and you add this extra branch. So this gives a recursive construction of this tree. And so that is called the Wilson's algorithm. And by the time you have finished running this procedure through all the vertices, and then you would have constructed the spanning tree. And it turns out that that tree has a distribution of this uniform spanning tree as well. So that's the Wilson's algorithm. So that's why I introduced a random walk, because you can use a random walk on this weighted graph to construct the uniform spanning tree. And now there's another model of spanning tree, which is called the minimum spanning tree. So in order to define the minimum spanning tree, we introduce a bunch of ID continuous random variables on the edges of the graph. So every edge on the graph is associated or is assigned one of these random variables, omega e. And we assume that these are continuous random variables so that no two edges have the same random variable. Then the minimum spanning tree is defined to be the spanning tree on this graph, which minimizes the summation of the edge weights, the edge random variables. And so that's why it's called the minimum spanning tree. So once you are given a realization of these edge random variables, omega e, then the minimum spanning tree is uniquely determined because of the assumption that these random variables are ID continuous. So there are no ties. So this is just an optimization problem. And in fact, it is not difficult to see that the minimum spanning tree actually is determined by the order among these edge variables, omega e. Once you know the ordering of these edge variables, then that determines the tree completely, and you don't even care about the precise values as long as order of these variables stay the same. So this is a fact that you can see again from two algorithms to construct the minimum spanning tree. One is called the Prim's algorithm. So the Prim's algorithm is a greedy algorithm where you build the tree one step at a time. So you grow the tree. So you start with one vertex V, and you look at all the potential incident edges, and you simply choose the one with the minimum edge weight. Suppose this one has a minimum edge weight, and you add this edge to the graph. So at some point, suppose that you have already constructed a tree that maybe looks like this. And then you look at all the incident edges to this graph that does not create a loop. And so among all the incident edges, you pick the one which has the smallest edge variable, omega e, and then you add this edge. For example, maybe this edge is the best, is the minimizing edge, the edge with the smallest variables that connects to this graph without creating a loop. And then you just add it. And so this is the next step of your construction. So you keep on doing this until you exhaust all the vertices of the graph so that you get a spanning tree. So that's called the Prim's algorithm. And another algorithm, which is also a greedy algorithm, is called the Kúsz algorithm. So in that case, you don't try to grow the tree. Instead, you look at the whole graph and suppose the whole graph, and you just look at among all the possible edges. And so among all the edges, you first find the one with the minimal variable omega e, then you add it to your construction. And then among all the other edges in the graph, you look for the next one that is the smallest. And as long as it doesn't create a loop, you add that edge to a graph as well. And so you keep on doing this. And so sooner or later, you would have created a spanning tree. And so that is turned out to be the minimum spanning tree as well. So that's an alternative greedy algorithm that constructs a minimum spanning tree. So here are some simulations by Luca. And so on the left-hand side, there is a depiction of the uniform spanning tree, and the right side is a depiction of the minimum spanning tree, and there are 100,000 vertices. And so the first impression you get is that the minimum spanning tree is a bit denser. And so the impression actually is correct. And at least on the complete graph, we know precisely what is the diameter of the uniform spanning tree and what is the diameter of the minimum spanning tree. So the impression that minimum spanning tree is a bit denser is actually correct. So what we are interested in is basically going to study the diameter of the spanning trees. And so here are some results I summarize in this table about the known results for the uniform spanning tree on different graphs, and also the diameter of minimum spanning tree on different graphs. So sorry, this one picture, sorry, I'm getting ahead of myself. This picture is just about uniform spanning tree. I'll talk about minimum spanning tree on the next slide. So on the complete graph, and as well as on dense graphs and the high dimensional toruses, high dimension means that dimension at least 5, then what is known is that the diameter is always going to be the square root of the number of vertices of the graph. And so high dimension is basically close to mean field model. A complete graph is a mean field model. So it's not surprising that all these models, they have a diameter that is basically the same. It's a square root of the number of vertices. In particular, they all converge as metric spaces, random metric measure spaces, to the so-called Aldous' continuum random tree. So they belong to the same universality class. And on the 4-dimensional torus, dimension 4 turns out to be critical dimension for the uniform spanning tree. And so there is a logarithmic correction. But once you take care of the logarithmic correction, then again, you converge to Aldous' continuum random tree. By the way, the superscripts here refers to the references below. And so you can check which result has been proved by which people. Now, in lower dimensional torus, the result is much less complete. So for example, in dimension 3, and it is known that there is a well-defined exponent which characterizes the diameter of the uniform spanning tree, but it is not known what is the number. And also, it is known that the uniform spanning tree on the 3-dimensional torus converges to a continuum limit. But I think the understanding of that limit is also somewhat limited. In dimension 2, this is the realm of conformally invariant models. And so their results by Kenyon, Lawler, and Werner, which basically characterize what is the diameter and what is the scaling limit. So this has to do with SLD. So that is roughly our present knowledge of the diameter of uniform spanning trees and their scaling limits. So here I don't care about the spatial embedding of the tree. I just look at the tree as a metric space by itself, where the distance is just a graph distance. In dimension 2, of course, you want to pay attention to the conformal structure, and so that has a lot to do with the spatial embedding. Now, for minimum spanning tree, much less is understood. And so what is known is that on the complete graph, the diameter is of order n to the power 1/3. Again, n is a number of vertices. So therefore, the diameter of the minimum spanning tree on the complete graph actually is much smaller than the uniform spanning tree. So that's why the picture of the minimum spanning tree looks a bit denser. And the scaling limit has been identified by Luigi Adalberri, Nicolas Bourdin, Christina, and Grégoire Mimont. And so this scaling limit is something that has to do with Aldous continuum random tree as well. But the object is a bit more complicated. And so for results on D-dimensional torus, I think there's much less is understood. So the natural conjecture is that in high dimensions, it'll be similar to the complete graph. but I don't think there are any results of this type. And of course, for the scaling limit, one can make the same conjecture as the complete graph, but again, there are no results. And as for dimension 2, there is a result by Gabin, Petit, and Schramm, where they look at a variant of, it's not exactly a minimum spanning tree on the graph. First of all, they consider triangular ladders in order to use the integrability of basically percolation on the triangular ladders, side percolation on the triangular ladders. And secondly, I think they look at a slight variant of the minimum spanning tree. It's not exactly the usual minimum spanning tree. And they are able to identify the continuum limit, which has to do with the invasion percolation on the graph. But I don't think they look at the diameter. Okay, so minimum spanning tree on the d-dimensional torus or the d-dimensional boxes, I think this is a particularly challenging problem. And so this also has to do with, I think, spin glass. So Chuck Newman had some lecture notes explaining the connection between minimum spanning trees and spin glass. So there is some conjecture of what is the critical dimension, whether there is a transition in the dimension in terms of the number of ends, if I remember correctly. And some people believe that it's 6, some people believe it is 8. And I don't know I don't think there are really rigorous mathematical results on this. Okay, so now let me come to the model that we consider. And basically, we are motivated by the study of directed polymer in running environments, which is a model that interpolates between random walk and last passage percolation. And so you can, if you're familiar with the directed polymer model, then you can see the clear analogy between the model we introduced on spanning trees and the directed polymer model. So I should mention that this model actually was introduced independently and simultaneously by a student of Gabopete, English Kúsz. And so it's by chance that we discovered that we actually came up with the same model with essentially the same results at roughly the same time. So it's quite a coincidence. Okay, so now let me introduce this model of running spanning tree running environment. So basically, you should think of it as a disorderly system, just like the directed polymer model. So by disorderly system, I mean that there are 2 layers of randomness. First, I introduce a running environment. And given the running environment, then I have the randomness of the spanning tree. And so here the running environment is given by a bunch of ID uniform random variables on the interval 0 to 1. So we choose this uniform distribution just for simplicity. And you could also choose other distributions. So here we just take a uniform ID, uniform distribution, uniformly distributed random variables, and assign to the edges. So we think of this as a disorder or running environments. And given a realization of this disorder or running environments, we are going to define Gibbs measure on the space of spanning trees on the graph. And so for Gibbs measures, typically we introduce inverse temperature beta, which specifies the strength of interaction between your spanning trees and the running environment. And so what we do is that given realization of the disorder omega and given the value of inverse temperature beta, then we define a spanning tree measure in the following way. So the probability that you sample a particular tree is going to be proportional to the product of the edges in the tree, and then for each edge you assign weight of e to the power minus beta omega e. The reason we do that is that you can think of it as e to the power minus beta summation e in the tree of omega e. So therefore you can think of this as the Hamiltonian of the tree in this running environment omega. And so Hamiltonian is essentially like the energy. So therefore, you are trying to weigh the probability of the tree according to this Gibbs weight. And so that's a natural way to think about it. So this is our measure for the random spanning tree in running environment with the parameter beta. And again, to make it a probability measure, you need to define normalizing constant. So that's the partition function. And now what is interesting about this model is that it interpolates between the uniform spanning tree and the minimum spanning tree. For example, if I choose beta to be 0, then these edge weights, these exponential weights become identically equal to 1. So this means that every tree has the same weight. And that's exactly the uniform spanning tree measure. On the other hand, if I send the beta to infinity, then you see that basically this probability distribution is going to concentrate on the tree configuration on the spanning tree, which minimizes the Hamiltonian. And so that's exactly the minimum spanning tree. And so therefore, as beta varies from 0 to infinity, we are actually interpolating between the minimum spanning tree, the uniform spanning tree, and the minimum spanning tree. And so that's exactly similar to the directed polymer model, where the reference measure is a random walk measure. And so when beta equal to 0, you just get a random walk. But the Hamiltonian is basically the summation of a bunch of random variables indexed by space-time that you see along the random walk trajectory. So therefore, when beta is equal to infinity, you want to find the optimal random walk trajectory, which basically minimizes or maximizes, depends on the sign you choose, of the edge of the weights that you see, of the disorder variables you see along the random walk trajectory. And that's the last passage percolation model. And so that's basically the analogy. And so you can also see that this edge weight, this weight of the tree is basically a tree of a uniform spanning tree on a weighted graph, and where the weights of the edges is just the exponential of beta omega e. So these are basically the weights I assign to the edges. So just to avoid confusion, I'm just going to call omega e to be the disorder variables, and while the exponential of minus beta omega e, I call it the edge weights. Okay, so our original motivation for introducing this model is basically just to introduce this interpolation. And because the directed polymer model, we saw phase transition, and which goes from the random walk behavior to last passage path, which is super diffusive. So we are hoping to see a similar transition that allows you to see that how you go from something similar to a uniform spanning tree to something that is closer to minimum spanning tree. And for that, we want to understand that what is the nature of this transition, and at which values of beta or the inverse temperature do you see this transition? And another question that is natural is that in order to talk about transition, you need to pick a physical observable order parameter. So what is the right order parameter that allows you to see this transition? And so one possibility is the diameter, because we already saw that the minimum spanning tree and uniform spanning tree on the complete graph, they are very different diameters with different exponents. So therefore, the diameter is one natural quantity. And you could also ask about, say, Hausdorff dimension of this metric space in some sense. Or you can also look at the local observables, such as that if I sample a local observable in the sense that like a local limits, for example. I pick a vertex at random and I look at a tree from this local point of view. And so what is the Benjamini-Schramm or local graph limit? So these are different possible observables one could consider. And then, of course, interesting question is once you have identified what is the diameter, then you could ask that is there a non-trivial scaling limit? And so as you observe this transition from uniform spanning tree to minimum spanning tree, ideally you would like to sort of characterize the set of possible scaling limits that interpolates between the scaling limits of the UST and the MST. So therefore, there are many questions which are open to this line of research, and so we basically just started this line of investigation. And as you'll see that our results are somewhat limited, and so yeah, I'll come back. I'll come to that shortly. So for our results on the diameter, we are focused mainly on the complete graph, and the reason is because for the complete graph, we have a fairly good understanding of the diameter and the scaling limits of the UST and MST on complete graphs. If you take any other graph, then our knowledge of especially the MST, the minimum spanning tree on such graphs are much more limited. And so therefore, the complete graph provides a good starting point to investigate this question of transition between UST and MST. Okay, so here is our first result. So the first result considers actually shows that the transition from UST to MST as far as the diameter is concerned actually doesn't occur at any finite values of beta. So if I take a complete graph with n vertices, then in order to see a change of diameter from square root of n to something much bigger, you need to choose a beta that grows with the number of vertices. So as long as the inverse temperature is smaller than some constant multiple of n divided by log n, then you can show that actually the diameter is still of order square root of n, same as the UST, with the beta equal to 0. So this first result suggests that the transition actually must occur at a value of beta n that is growing with the number of vertices and has to grow faster than n over log n. So we call this regime to be the low disorder regime, because in that sense, the disorder is not strong enough to change the diameter's exponents. There's a side result we obtained. So here our result is formulated in terms of these Gibbs measures. And so there's a side result that we obtained first, which is to say that let's forget about beta. Let's just fix an arbitrary distribution on the edge weights, which are ID random variables. And we show that in that case, if you have the expanded graph with a bounded maximum degree, or if you have the torus, then basically the diameter is of order square root of n, modulo some logarithmic factors, which are probably not sharp. So in connection with the previous result I introduced on the random spanning tree running environment, you can think of it as saying that for in a fixed beta, if I fix beta, so it doesn't change with the number of vertices, then the edge weight distribution is not changing. And so here we are just saying that if we pick in a generic edge weight distribution, then basically we have the result that diameter is of order square root of n for not just the complete graph, but also for expanded graphs with bounded degree, and also for torus of dimension 5 and higher. Okay, so the bound on the diameter is basically square root of n, but there is some logarithmic factors hanging around which are probably not sharp. Okay, so that's sort of a side result we obtained first before we posted the paper on the random spanning tree running environments. The proof of both of these results, which are basically saying that diameter is of order square root of n, similar to the uniform spanning tree on the complete graph and high dimensional graphs. The proof of both results are based on the extension of criterion formulated in a paper by Michaeli, Nachmias, and Shalev. But their criterion was for graphs without varying edge weights. And so what we did is that we extended their criterion to the case where the edge weights may vary. Okay, so that was the low disorder regime. And now let's look at the high disorder regime, where the diameter is going to be the same as the minimum spanning tree, or at least up to leading order. So I should mention that, as I mentioned before, that most of the results are basically done concurrently by us and by Agnes Kúsz. So this paper here. So they appeared basically within maybe 1 or 2 weeks of each other. Okay, so what I refer to the high disorder regime is when beta n is larger than n to the power 4/3 times the log n. And so here we see that exponent is no longer 1. In the low disorder, it was n over log n. In the high disorder, now it's n to the power 4/3 times the logarithmic factor. So in that case, we can show that with high probability, with respect to the joint law of the running environment and the law of the uniform spanning tree in that running environment, we can show that diameter is basically within constant multiples of n to the power 1/3. So we call this the high disorder regime of this model. And so this basically leaves open the question of what happens in between n and n to the power 4 thirds. Let's forget about the logarithmic factors because these may not be sharp. And let's just focus on the exponents. So for inverse temperature that is between n and n to the power 4 thirds, we conjecture that the diameter is going to change with the beta n. So if you assume that beta n, the inverse temperature, is of the form n to the power 1 plus gamma, the gamma is between 0 and 1/3, we have a conjecture that the diameter of the random spanning tree will be of the form n to some power, and the power basically is linear in the power exponent of beta n. Okay, so I'm not personally, I'm not super confident of the validity of this conjecture, and but I think it's good to suggest something and put it on the table, and hopefully this will spur people's interest. So, but I think maybe Luca or Michele, they have more confidence in this conjecture. They can explain it later. Okay, so let me explain now. Let me explain a bit of the proof ideas of some of these results. So as I mentioned before, if you want to show that the diameter of the spanning tree the diameter of this random spanning tree in this random environment in the low disorder regime is of order square root of n. What we are going to do, what we did was that we extended a criterion of Micheli, Nachmias, and Shalev. So let me just review that what are the ingredients of this criterion. So there are three pieces, and the first piece is to say that, so we call it balance, it's called a balanced, and it is basically saying that if the edge weights are not constant, then what we should look at is the following. For each vertex u, I can look at the summation of all the edge weights incident to that vertex. And so I want to compare the worst case, the maximum, and the minimum. So among all vertices, if you look at the total edge weights incident to that vertex, I want them to be sort of bounded within constant multiples of each other. And so that's what this first condition balance is saying. So if it was a graph, it is basically saying that the maximum degree and the minimum degree of all the vertices are basically within constant multiples. And so that's this first condition. And the second condition is about the mixing time of this random walk on this conductance network. And we want the mixing time to be of an order that is a bit smaller than square root of n. And so alpha is a positive number, and so you want the mixing time to be a bit faster than square root of n. And the third condition is about the return probability. The return probabilities. So the transition probability from a vertex back to itself at time t. And so you want some uniform bound over all the vertices. And I want I want basically the transition probability from vertex back to itself to decay sufficiently fast in time. And but I only care about what happens up to the mixing time. And so that's called escaping, because somehow you want to run, you don't want the random walk to come back quickly. You want the random walk to somehow escape. And so this is the third condition. This is the third condition. Yeah, so this introduces a bunch of three constants, d, alpha, and theta. And so the criterion, so basically the result says that once you have identified these three numbers, d, alpha, and theta, then you can basically identify a constant c depending on these three parameters, so that the diameter is essentially of order square root of n with a constant multiple that depends on this c. So in particular, if d, alpha, and theta are uniform for a sequence of graphs, then basically you're saying that the diameter is essentially of the same order as along this sequence of graphs. Because here we are always considering a sequence of graphs with a number of vertices is going to infinity. So therefore, the dependence on c on these so the important thing is try to control these three parameters and show that they are uniform throughout this sequence of graphs. Okay, so that's basically the criterion that we applied in order to get this square root of n order for the diameter in the low disorder regime. Okay, so Now, in our actual application of this proposition, the first condition is typically violated because we are going to choose edge weights W to be of the form e to the power minus beta omega e, where omega e is a uniform random variable on the interval 0 to 1, but the beta is going to infinity. And so therefore, we cannot immediately apply this proposition to our model of random spanning tree running environment because the quotient is no longer guaranteed to be bounded. And so therefore, we need to use additional idea. And so the additional idea is basically to do some sort of truncation. And so what we can do is the following. Suppose that you have a weighted graph where the edge weights or conductances are ID random variables with some distribution on the interval 0 to infinity, which is not assumed to be bounded. We don't assume that it has bounded support. And so what we can do is that we can do some sort of truncation. So I pick a number A, very large, and I only focus on conductances which lie in the interval from 1 over A to A. But what you do with the edges where the conductances are outside this interval? So what you do is that we first condition on the uniform spanning tree on the edges where the conductances are either very small or very large. The reason for doing this is that if you have a spanning tree, uniform spanning tree on the graph, and you know that a particular edge is conditioned to lie in that uniform spanning tree, then you can basically contract that edge and to make it a single vertex. And what is known is that if you look at the conditional distribution of the uniform spanning tree on the remaining edges on this contracted graph, then it is still distributed as a uniform spanning tree. And similarly, if you know that a particular edge is conditioned not to lie in that uniform spanning tree, then the effect is the same as just removing that edge from the graph. And the conditional distribution of the uniform spanning tree is simply that on this modified graph with this removed edge. So therefore, if we first condition the uniform spanning tree's configuration on this set of bad edges, then we can basically do some contraction, do some deletion, and then we end up with a new graph. And on that new graph, we basically have a good control on the edge weights because most of the edges will be, the edges themselves, they will lie in this interval. The edge weights will lie inside this interval, so they're bounded. The only complication that after you do the contraction, then maybe you'll create multiple edges. Between two vertices, there'll be multiple edges. But you can control that what is the multiplicity. The multiplicity basically introduces some logarithmic factors. And that is still something that we can control in this previous proposition. And so that's what's, yeah, so here there is no logarithm in the square root of n. But if these factors here, D contains some extra logarithm, then this will be reflected in the logarithm in the prefactor of square root of n. And so that's basically what we did. And so we do the conditioning on these bad edges, conditioning on the uniform spanning trees configuration on the bad edges, and then do the contraction deletion so that we get a better graph. And we bound the diameter of the uniform spanning tree on this better graph. And then we uncontract, undo what we did, undo the deletion, undo the contraction, which introduces some extra additional logarithmic factors. And so that's how we are able to show that even though the edge weights are not uniformly bounded bounded away from 0 and infinity, we can still get the square root of n diameter modulo some logarithmic factors. Okay, so that's the rough idea for the low disorder regime. And for the strong disorder regime, when the beta n is larger than n to the power 4/3, and we show that diameter is essentially of the same order as the minimum spanning tree on the complete graph, the basic proof strategy actually is quite basically adapted from what was done for the minimum spanning tree. There are some differences, but the overall strategy is essentially the same. So it relies on the following key lemma, which says the following. So the basic idea is try to look at the edge weights and you pick a threshold so that the high conductance edges essentially form a critical Erdős-Rényi random graph. And so you choose a threshold so that the high conductance edges are essentially a critical Erdős-Rényi random graph. And then using this as a base point, we pick a larger threshold so that you include more edges, you include the edge weights which are slightly worse. And if you do that, then you can basically create a subgraph of the Erdős. You can basically create a slightly supercritical Erdős-Rényi random graph that is connected. And so the basic result, the key result is to show that if you want to look at the diameter of this random spanning tree random environment in this for such choice of beta, then it basically boils down to look at the spanning tree restricted to this giant component of this slightly supercritical Erdős-Rényi random graph. And so that is the key point. And yeah, so P1 is exactly choosing the critical window, as I mentioned before, and P2 is something that you pick a slightly larger. So I should be a bit more precise of how do we choose P2 and why do we choose P2 minus P1. So P2 minus P1 is of this particular form. Why do we choose P2 minus P1 to be of this form of C log n over beta n? So you can see this from the following calculation. Basically, it is saying that if you have a vertex U and V, and they are connected by edge that is in the P1 cluster, so this is has a parameter P1. P1 basically refers to the threshold. P1 is a threshold for high conductances or high edge weights. So this is reflected in the omega random variables. So omega is in the interval 0 to 1, and P1 is a threshold. P1 is a threshold inside the 0 to 1 as well. And so you translate the P1 back to the edge weights, here. Okay, so why do I choose P2 minus P1 to be of this, the gap between P2 P1 to be of this value? And the reason is the following. So if I pick a edge UV, which is connected where the edge weight is sort of good enough, is associated with this threshold P1, then the claim is that in the in the random spanning tree, it doesn't make sense for you to, okay, let me draw it here. UV. So if this is a good edge with which is above this threshold P1, then it doesn't make sense for you to go around and try to pick an edge in the uniform spanning tree where this edge is much worse in the sense that the omega random variables differ by a gap of C log n over beta n. It doesn't make sense for you to pick a much worse to make a detour and choose a much worse edge and add it to your uniform spanning tree. So it is seen in this calculation here. So for example, I want to know what's the probability that this edge UV, so I know that what's the probability that UV belongs to the uniform spanning tree, this particular edge. And so there's a formula for edge to belong to a uniform spanning tree, and the formula is the following. First, you have the edge weight or the conductance of that edge. So the conductance is of the form e to the power minus beta omega UV. This is the edge weight. And then you multiply by the effective resistance between these two vertices in the graph. And so the effective resistance in the graph can be bounded from above just by choosing. You can find a particular path connecting these two vertices. And so if you compute the resistance along this particular path, then it already gives an upper bound on the effective resistance, because adding more connections will only reduce the resistance. So therefore, you can try to give an upper bound on the effective resistance. And so the path length is at most n on the complete graph. So that's where the n comes from. And then you have the worst case scenario of what is the conductance of the edges you see along the way. And so therefore, if you compare these calculations, then you see that you basically, the probability of doing this is actually bounded by n times exponential beta n times p2 minus p1. Okay, I think I'm not remembering precisely the details of the calculation, if my explanation is correct or not, whether it matches the calculation. But the basic idea is that if the edge has a good conductance, then it doesn't pay for you to go make a detour and pick up an edge with a much worse conductance. And how much worse is quantified by this constant here, which depends on the beta n. And so that is somehow the key result, which says that if I look at basically a Erdős random graph component, and the component consists of edges which are good, and then you want to ask that what is the subset of a spanning tree which connects, okay, let me draw a picture. Suppose that this is a component of the Erdős random graph with good conductances. And I want to know that what is the spanning tree that connects all the vertices in that disease graph. Now, in the minimum spanning tree, of course, it will just be restricted to this tree. If you are considering minimum spanning tree, it will just be restricted to this tree. But in this random spanning tree random environment, which is basically a uniform spanning tree on a weighted graph, they will make detours and go out of the cluster. And so that is the main difference between the minimum spanning tree and this random spanning tree random environment. Because when you consider the uniform spanning tree on this weighted graph, it will actually use the edges outside this cluster. But this result is telling you that you cannot use edges which are too bad. So therefore, that's why we slightly enlarge the threshold. And so to make sure that when you consider the edges in the uniform spanning tree that connects these vertices, they don't go too far. And they only go to basic clusters where the edge weights are slightly worse. And so this creates some sort of recursive structure, which allows you to control the diameter in a recursive fashion. And that part of the argument is then similar to what was done for the minimum spanning tree. Okay, yeah, so essentially it's saying that by this argument, you can essentially only look at the uniform spanning tree restricted to some sort of giant component in the slightly supercritical population model on the complete graph. And then what about the vertices which are outside this giant component? Well, then you can use the Wilson's algorithm to show that they will quickly hit this giant component and they will not really make an additional contribution to the diameter of the tree. So that's the rough idea. Okay, so yeah. So in the case that when the beta n is much larger than n to the power 4 thirds, essentially what we can do is that you basically pick. I mean, when you start this argument, I start I start with essentially the critical population, critical Erdős random graph, which it has already diameter of all the n to the power 1 third. And then when you sort of try to look at what are the connections in the uniform spanning tree that connects these vertices, then you essentially add the extra layer, create a slightly bigger component, and then you keep on doing this. But every step along the way, you are essentially within the critical window. So that's why the diameter is still of all the n to the power 1 third. But when it comes to this window that we haven't understood, so I said that the region that we haven't understood is when beta n is much larger than n of log n and much smaller than n to the power 4 thirds, sorry, n to the power 4 thirds log n. So within this window, we haven't really understood what's going on. And now, why did we conjecture that the diameter is still of the form n to some power, where the power exponent essentially is linearly interpolating between 1 third and 2 thirds? And the reason that we came up with this heuristic is because we can try to do a similar argument. I start with a threshold that is slightly supercritical Erdős-Rényi random graph. And I choose it sort of in a way to make sure that the diameter of the uniform spanning tree on this the diameter of the random spanning tree running environment on the complete graph is essentially the diameter of this random spanning tree running environment on this slightly supercritical population model. And so on this slightly critical population model, we can use the structural results for this Erdős-Rényi random graph. So that's a result by Ding, Perez, I think maybe Jing, they're a Korean researcher. And so they are basically saying that you can identify sort of the core. There is the core of this giant component. And so there are a lot of danglings. And then between the core, in the core, essentially you have long strings of these edges. And so you can sort of reduce the structure of the graph to something that is simpler. And on that simpler graph, in certain parameter regimes, it's a random d-regular graph. In other regimes, it's a mixture of random d-regular graph with different d's. And so our ansatz was basically saying that if I look at that graph and the edge weights are essentially, there's the law of large numbers, right? Because there is a string of edges which essentially serve as a single edge in this in this core. And so there is a law of large numbers, so the edge weight distribution is a bit more concentrated. So therefore, it's a bit more like a usual graph with constant edge weights. So therefore, our ansatz was to say that we need to look at the diameter of the uniform spanning tree on this new graph. And so if the edge weights were really constant, then the diameter would just be the square root of number of vertices. And so if we make this assumption, then you come up with the conjecture that we made. Yeah, it's in some sense, it's more of a guess than a high confidence conjecture, I would say. Okay, so in the last few minutes, let me just mention there is results on local limits, local properties. So before I talked about diameter, but you could also look at the local observables. And so that's results by Luca and independently some of the results by Agnieszka as well, where they show that in contrast to the diameter, where we have this window where we conjecture that the diameter is changing continuously, for local observables, actually, they can show that there is a relatively sharp transition. And the transition occurs around order n, the transition occurs around order n. So what are the local observables we are looking at? So one of them is simply the summation of these disorder variables along the edges, or the Hamiltonian. And so when beta n is much smaller than n over log n, then the expected value, so here expected value of the tree, given the running environments. So the expected value of the Hamiltonian is essentially n over beta n. And the second observable is the so-called overlap. Overlap means that given the realization of the running environment, I sample two independent trees in the same running environment, and I count what is the number of overlapping edges. And you can see that this is the same as going through each edge and ask what the probability the edge belongs to the tree, and then you square it. So that's why it's a local observable, because you are looking at for each edge, and then you are summing over all the edges. So in this regime, when beta n is much smaller than n over log n, the expected overlap is of order beta n. And furthermore, if you look at the local limit, then they have shown that the local limit actually the same as the local limit of the uniform spanning tree on the complete graph. On the other hand, if you look at the regime where beta n is much larger than n times some powers of log n, then there is a distinction. So before the Hamiltonian, expected value is n over beta n. So in particular, this is diverging for this choice of beta n. But now you see that the Hamiltonian is going to be essentially a constant. So that's a Riemann-Zeta function at the value 3, at argument 3. And similarly, for the overlap, you find that the overlap now grows with order n, while before it was beta n, which is much smaller than n over log n. And also the local limit is now going to be the same as the local limit of the minimum spanning tree on the complete graph. And so that's a relatively sharp transition modulo some logarithmic factors. And so that's quite interesting and complements the result on the diameter. Because for the diameter, our knowledge, I mean, there's still a bigger gap. And we don't even know. So first open question. So let's ask a more modest question. Instead of trying to prove the conjecture, how about finding a sequence of beta n diverging such that you can show the diameter is really n to some power that is different from 1/3 and 1/2? And that is a much more modest question. And for the moment, we don't have an example of this. We don't have a result of this nature either. And so closely related question is to look at the volume of the metric ball. So I pick a vertex at random, and I look at a ball of radius r centered at the vertex. So as r increases, how does the volume of the ball grow? The number of vertices in that ball, how does that grow? So this should be related to the Hausdorff dimension of, say, the scaling limits. And so these are interesting questions to investigate. And another question that I was curious about is that if I interpret the Hamiltonian as similar to the eigenvalues of random matrix, what can you say about the point process, like especially near the edge? In the bulk, I expect it to be simpler, but at the edge, maybe there's something interesting. So what can you say about the point process of these Hamiltonians indexed by the tree? And especially this would could potentially give another way of looking at the diameter, because near the edge, there's a minimum spanning tree, but or some variations of it. And how does the diameter vary as indexed by these points near the edge? And of course, one can ask about the random spanning tree on the running environment on different graphs, and also on the torus. So one of the hope is that maybe by understanding this interpolating model a bit better, one can also understand the minimum spanning tree a bit better on the on the torus. So I think that's all I want to say. And yeah, I conclude with a tree.
Thank you very much, Rongfeng, for a fascinating talk. So I'd like to open it up for questions. Please feel free to either kind of wave or unmute yourself. I think Alex has a question, so I'll start with him.
Yeah, thanks for a fascinating talk. I wanted to ask about so local limits. You talked about raised the question of random deregular graphs at the end. So for the local uniform spanning tree, it's sort of this very robust result that you get this sort of +1 branching conditioned on survival. And so you said in the complete graph that holds beta all the way up to n over log n. Do you think something similar will be true for deregular graphs? All deregular graphs if D grows?
Okay. Yeah, that's a perfect question for Luca, because this is Luca's result.
Yeah, so I think it should hold. You replace n with a degree. So if it's deregular, beta is less than d over log n or something like that. It should still hold.
Okay, nice. Thank you.
Julien? He's waving at me. So.
Yep. So I think I just want to go back to your first question in your last slide about the scaling limits. So do you have a guess for what happened between the Aldous CRT and Christina's scaling limit?
I would say no. I mean, we can take our conjecture. You can take our conjecture if you really believe our conjecture, and how we came up with the conjecture. Then I think you can sort of make a guess on the scaling limits, because the conjecture will say that you go to this the giant component of this slightly supercritical population. You sort of trim away the long edges, trim away the leaves, and then you have some sort of mixture of a random deregular graph. And so in that sense, you can sort of make a conjecture on the scaling limits. But as I said, I'm not very confident about conjecture.
Thanks.
Is there a sort of simple intuition why something happens at n to the 4/3? Because n is kind of intuitive, because that's locally, when the smallest weights around a vertex start competing with each other significantly or something. But n to the 4/3, it sort of comes out of all these calculations. But is there an intuition?
Yeah, I think let me try to go back to this key lemma. So there is this key lemma I stated. Okay, here. So in the key lemma here, I think if we pick a beta n to be n to the power 4/3, and P1 is in the critical window, then you'll see that you're basically in the critical window where the graph becomes connected. I think that's something that you saw in the we saw in the minimum spanning tree paper as well. So in minimum spanning tree, there is some sort of recursive argument. You're in the critical window, so it's always 1 over n plus lambda over n to the power 4 thirds. But once the lambda reaches of all the log n, then the graph becomes, then you are essentially exhaust everything you need to know about the diameter of the minimum spanning tree. All the additional vertices, when you try to connect the minimum spanning tree, they don't really add to the diameter. And so that's why beta n equal to 4, so n to the power 4 thirds actually appears because it's exactly correspond to, in the critical window, you choose lambda to be of order log n. So it comes from this key lemma.
Okay.
Because this key lemma is essentially the tool that allows us to sort of start with a critical order Schrödinger random graph. Then, in order to construct the uniform spanning tree connecting vertices, we need to enlarge it, and then we need to keep on doing this. So in order to make it work, we need to beta n to be essentially of order n to the power 4 thirds or larger.
And so what is it that tells you that this critical graph is somehow enough to get this structure?
Why does it you mean that why we start with a critical window and then we sort of keep on increasing the threshold? Why does it
if you start with a large enough P, then you've included sort of most of the structure or something. So it's quite surprising that you can take this P that's so small that you've only got into the 2/3 of the vertices. I guess the one that
I think yeah, so that argument was already used in the minimum spanning tree paper, and I think it has to do with the balance between sort of okay, let's think about this uniform spanning tree setting. In the uniform spanning tree setting, you apply Wilson's algorithm. And so if you pick a vertex that is outside this giant component in the slightly supercritical window, then it is going to hit this giant component fairly quickly.
Yeah,
And,
okay. Like n over the size, so n to less than n to the 1/3. Okay, yeah. Or something.
Yeah, so that's the heuristic, yeah.
Thanks.
Any further questions from the audience? Just a comment from Luca in the chat. That's very helpful.
Yeah.
I maybe want to just add one to your list of kind of open questions, which I think are maybe sort of approachable. Maybe even before doing the diameter, how about just the typical distance?
Yeah, that's right.
Rather than dealing with sort of
exactly. Yeah, diameter is asking also quite a uniform upper bound. Why not just take two randomly chosen vertices and ask what is the distance between the two? Yeah. And I think another question that Luca has been studying with Umberto D'Ambrosio is try to look at maybe a toy model. So one of the difficulties in studying this is that we pick the omega e, the disorder random variables, to be uniform. The problem is that when beta goes to infinity, essentially it's going to create a sort of separation among the different values. And so if I pick any two edges and I look at the quotient of the edge weights, then it's either going to 0 or going to infinity. And so it's kind of creating some sort of separation. And so essentially there's infinitely many scales if you want. And so therefore, I think what the Luca and Umberto study is that let's consider a simpler model where the edge weights only take, I think, 2 values or 3 values. And so as the beta n goes to infinity, you still see this sort of separation, but it's only when the edge weights are different. So essentially you create sort of a much simpler structure. And ideally, if you understand this for maybe 2 edge weights, 2 valued edge weights or 3 valued edge weights, then potentially you can also discretize the omega e in the interval 0 to 1 into discrete pieces. And so that's one long-winded way of maybe try to tackle the problem. Of course, you can ask Luca for more details. What is the progress in this direction?
Yeah, there's almost too many degrees of freedom in the model at the moment because you've got the weight distribution. So
the edge weights Yeah, the edge weights are getting too different from each other because yeah, some edge weights are just too low, some edge weights are too high, and there is not a single scale which you can pin them down. They are all over the place, and that somehow creates the difficulty.
Right.
But if anyone can make progress on this, it'll be great.
I think that's all of the questions. Thank you very much, Rongfeng. That was a lovely
Yeah.
talk and really stimulating. And thanks also to Luca for coming along and joining us. Very
I
nice.
don't know if Michele is here.
Michele's made it.
Okay, yeah, thanks for the invitation, and yeah.
Let me stop recording, and then what I suggest is that everybody unmutes and that we overwhelm Zoom with applause.